Now that we have been introduced to the factorial notation, we're ready to learn how to count permutations. When more than one item is selected from a single category and not replaced, and the order of selection is important, the outcomes are called permutations. Now, stop for just a minute and contrast this with what we've learned about the fundamental counting principle. In the fundamental counting principle, we were choosing one item per category. Remember the pizza that we counted, how many different choices of pizzas we had? We were choosing one topping for that decision. What if I want to choose 2 or 3 or 4 toppings? How am I going to be able to count that? So we will use a permutation when more than one item is selected from a single category. This is how a permutation is different from the fundamental counting principle. Now, another important thing to understand about permutations is that the order of selection is important. Now, this is not going to apply to our pizza because it doesn't matter the order in which we place the toppings on our pizza. It's still going to be the same pizza. So this is how we're going to contrast it from combinations. So if the order of selection is important, it's going to be a permutation, but this is how it is different from a combination, which we'll learn in section 11.3. Okay, so for now, to count a permutation, we're realizing we're going to select more than one item per category, and the order is going to be important. Now, if you're unsure at this point, that's okay. We're going to do a lot of examples to further develop this concept. Here's a great example to get started. We're going to list all possible 3-letter permutations of the set MATH. Notice that is a set in roster notation. The cardinal number of that set is 4. Remember all this good stuff? Because that set has 4 elements. And so we're going to create 3-letter subsets, and we're going to figure out how many different permutations we can make. Now, one possible permutation, and we're not going to write this in roster notation, we're just going to write words. One 3-letter permutation, think of the word permutation as arrangement. One possible 3-letter arrangement or permutation of the set MATH is MAT. Now, think about words. Words are actually permutations of our letters. What happens if I switch the order of the letters? Do I get a different word? Absolutely. In fact, if I tried to write mat and I wrote MTA, my teacher would say, hey, you misspelled that word, right? So if I rearrange the order, I get a different word. So the order of selection is important. That means when I change the order, I get something new or different. So let's consider all of the 3-letter permutations that begin with M. Another possibility would be M, T, and H. I'm going to switch those last 2 letters, M, H, T. Now I can think of 2 more that begin with M. How about M, A, H, and M, H, A? So I'm trying to do this systematically. That is, I'm figuring all the 3-letter permutations that begin with M so that I don't leave anything out. Let's think about all 3-letter permutations that begin with A. I'm going to start with A, M, and T. So if I switch the order of the last 2 letters, ATM, I get a completely different permutation. How about ATH? And then again, AHT. And there should be 2 more that begin with A. AMH and AHM. Let's come up with all the 3-letter permutations this time that begin with T. We could go with TMA or TAM, right? How about TAH and THA? And then finally, THM and TMH. So we can finish with all the 3-letter permutations that begin with H. HAM HMA, HAT, HTA, HMT, and HTM. I think we got them all there. So those are all possible three-letter permutations of the set math. Now think about our language. Our language, the words that we form, are simply permutations of the letters of our alphabet. We have three-letter permutations, four-letter permutations, so on and so forth. Now, if I have a larger set, in this case, the cardinal number of our set was 4. If I'm looking at the alphabet, the cardinal number of that set is 26. How many three-letter permutations could I have of the 26 letters of the alphabet? A lot, and we're not really going to want to take the time to list those. So instead of listing those, there is a formula for counting the number of permutations. Here's the formula for permutations. The number of permutations of n items, that's the total number of items that I have, taken r at a time, so that's the subset I'm taking, is given by, we're going to read this NPR, and it's equal to, I'm going to take the total number n factorial on the top, then I'm going to find the difference of the total and the number that I'm taking at a time, find that difference, and then evaluate that factorial. That's going to count the total number of permutations of n items taken r at a time. Now, if that looks familiar, that pattern looks familiar, remember up here on example 1C, that's the pattern that we practice evaluating. That's actually a permutation. Now, let's apply this formula to example 2. Use the formula to calculate the number of three-letter permutations of a set containing 4 letters. So the total number of letters we had to work with was 4 because the order of the arrangement made different words. We're dealing with a permutation here. And we evaluated, or we took them 3 at a time. So we need to calculate 4p3. So we're going to put a 4 factorial in the numerator. We have n factorial in the top. In the bottom, we find the difference between our two numbers, 4 minus 3, and then evaluate that factorial. So let's simplify. Remember, the order of operations is important. So I'm going to evaluate 4 minus 3 in parentheses first to get 1 factorial. Then we can expand those factorials. 4 factorial is 4 times 3 times 2 times 1. And 1 factorial, well, that's just 1. So we can evaluate this as 4 times 3 times 2. 4 times 3 is 12. 12 times 2 is 24. So 24 total permutations. Now, if we come back up here to example 2, we had 1, 2, 3, 4, 5, 6 items in the rows, and we had 1, 2, 3, 4 columns. So we got a total of 24 permutations. So what we painstakingly took the time to list in example 2, we were able to efficiently calculate at least the number of outcomes using this formula. Now, I've got great news for you. This formula is available on your calculator, and it's going to save you a little bit of work. So let me show you how to type in 4p3. So the first thing I'm going to do is type in the 4. That's the n, the total number of items I have to choose from. Then I'm going to go to this math menu. This is the same menu where we found factorial. And I'm going to use my right arrow key to highlight PROB for probability. Do you see it there? Option number 2, that's NPR. That's the permutation formula. Also observe number 3, there is NCR. That's a combination, and we're going to learn that in the next section. So for now, I want to choose the permutation number 2 because the order makes a difference, and press enter. When I get back to the home screen, I'm going to type in the R value, which is 3. The calculator plugs it into the appropriate formula and gives us the output, 24. Easy as that. We will practice that calculator process on the next few examples. Example 4. In how many ways can president, vice president, secretary, and treasurer be selected from a club of 30 members. So we have a total of 30 members in our club, and we are forming a slate or a lineup of executive officers for our club, and there's 4 for the slate, right? Now think about this. Does the order in which we choose these members make a difference? Well, if I choose you to be president, do you observe a difference than being chosen to be treasurer? Absolutely, there's going to be a difference in your job description. So the order of selection does make a difference. So if I have 4 names listed, person A is going to be president, person B is going to be vice president, so on and so forth. That's one possible slate. But if I switch these 2, it's a different setup. It's a different government for our club. So the order of selection is important. And the reason I'm stressing that is because it makes it a permutation. We will contrast this with a combination in the next section where the order doesn't make a difference. So we have a total of 30 members, and we're selecting them 4 at a time, and the order is important. So we'll evaluate 30p4. So from our calculator, we're going to type in 30. That's the N value. We go to our math probability menu and select option 2. We're going to enter our R value, which is 4, and evaluate. So we get 657,720 different ways. 657,720 possible slates. That seems like a lot of possibilities from just a club of 30 members. Now, a quick little note, another way to think about this problem, permutations and the fundamental counting principle are often related. Another way I can think about this problem is through the fundamental counting principle. We learned we've got a series of 4 decisions to make, right? Who are we going to choose for president? Well, at first, we have a total of 30 members to choose from. Now, when I choose a person for president, that person is no longer available to serve the office of vice president. So that leaves 29 students possible for vice president. When those 2 spots are chosen, only 28 members are eligible for secretary, and then finally 27 for treasurer. Notice what happens when we multiply these numbers together. 30 times 29 times 28 times 27. We get the same result. 657,720. So you can view this either as a permutation, that is, you have a total set and you're selecting them 4 at a time and the order matters, or you can view it as you have a series of 4 individual decisions to make, and then you can count the number of choices for each decision. So the permutation is built on the fundamental counting principles, just kind of a different perspective. Let's try one more example. In how many ways can first, second, and third prize be awarded in the Miss America Beauty pageant with 51 contestants? So let's think first of all, does the order of selection matter? If you're in this beauty pageant, do you care if you get first or second or third? Yes, your position makes a difference, right? So order matters, therefore it is a permutation. So one way to think about it, I have 51 total contestants, and I'm going to figure out how many different slates, how many different ways can we choose first, second, and third prize. So I'm going to choose the top 3 from 51. So entering this into our calculator, we have 51, math, probability, option number 2, permutation, selecting 3 at a time, 124,950 different possible ways. That's a lot of possibilities for 51 people. And again, you can also think of it as fundamental counting principle approach. Remember, that's called FCP, fundamental counting principle, just an option. To select the person for first prize, you've got 51 contestants to choose from. Once first prize is selected, then only 50 are available for second prize and 49 for third prize. So 51 times 50 times 49 yields the same output. So either way you want to look at it, choose the path that makes the most sense to your mind. What's most convenient? So again, a permutation, we're selecting more than one item per category, and the order is important. Practice that with your calculator, and we'll look at a variation on this in the next section.